Okay, so today we're going to talk about how to linearize data like a physicist. So I'm going to start by telling you kind of a story about, I used to live with this kind of crazy lady. She was very nice, but a little bit crazy. And we were talking about how to do data analysis as a physicist. And here's the thing about it, it's really easy. Your data should be a line. So if it's not a line, it's not good data. It's a lot easier than sometimes biology and social sciences and things like that, because in physics, an atom is an atom is an atom. They should all behave the same way, right? If our laws are good, your data should turn into a line, and that's pretty much all there is to it. So, what if it's not a line? Well, you need to make it a line. Okay, so let's do an example. So if we're taking data on position versus time, so we're going to put position on our y-axis and time on our x-axis. And I get some dots that look like this. I can draw a line through it, a best fit line. And then the slope tells me the change in position with time, which we'll learn later on is called the velocity. So the slope of that line gives me the velocity. So that's a really simple example of how to take data and show that it's a line. Then we can look at the formula. The formula is x equals vt. So position equals velocity times time. And what is the equation of a line? Well, we know that the equation of a line is y equals mx plus b. So importantly, I'm missing the plus b part, right? So what is the equivalent to that? Well, what is my position at time t equals 0? We call that my initial position, right? So I started at something not 0. I could have started at 0, but in this case, I started at something non-zero. So that gives me an initial position. So what we're doing is whatever equation we're using to study, we want to make it look like y equals mx plus b, because that's the equation of a line. So in this case, we're using the position at any point in time equals the velocity times time plus the initial position. And that corresponds to y equals mx plus b. So that means if you plot y versus x, or in this case, position versus time, the slope gives you the velocity, and the y-intercept gives you the initial position. So this is probably the simplest example of this you can do. So I was talking with this friend about how to do data analysis, and she was asking me some questions, and I said, it's really easy. You just plot everything on a line. And she said, okay, what if your data is not linear? Because not everything is a linear relationship. And I said, okay, well, that's easy. You just plot stuff until it becomes linear. So a really good example for that is Kepler's third law, which says that the period of something orbiting something else, the period squared equals 4 pi squared over a constant g, the mass of whatever is being orbited, and then the distance cubed. You will learn this law later on, but don't worry about it for right now. Just looking at that formula, it doesn't seem like it's a linear thing, right? So if I just plotted t versus r, I would have to take the square root of both sides, and I would get something that goes t is equal to something times r to the 3/2, and I would get this funky curve thing. So that's not a line. So what do I need to do to plot it to make it linear? Because we don't want to do that. We want to make it a line. So this time, let's look at our equation, and let's say, what can I plot to make it linear? So I'm going to write y equals mx plus b under it, and thinking about it this way, that tells us that if we plot t squared on the y-axis and r cubed on the x-axis, then our slope is going to be 4 pi squared over gm. So I'm putting my things on the axes. And now I should get data that looks like a line. And in this case, my y-intercept is actually 0, because in this formula there's no other term. It might not be exactly 0 because of experimental error, but it should at least be pretty close to 0. So let's look at some examples. Oh, whoops. Apparently that didn't work. Okay. I had some examples of some graphs where I did this, but they're not showing up right now, so we're just going to go with it. So let's apply what we just did to the pendulum data. So the formula for the period of a pendulum is actually 2 pi times the square root of L over G, where G is the acceleration due to gravity and L is the length of our pendulum. We didn't really talk about that, but That's what it is. So let's rewrite it so that we separate off the square root of L. So we can do that with square roots. So we'll put the square root of G over by itself and the square root of L by itself. And now we're going to do our y equals mx plus b thing again. So looking at this, we should plot t versus square root of L. And then 2 pi over square root of G should give us our slope. So when we do that, we should get a line, right? And our slope is going to be equal to 2 pi over the square root of G. So that's a way of, if you do this and you find the slope, you can find what the value of G is on Earth. You just are going to solve for G. There's another way to do it. One way to do it as well is to square t squared. And then you get 4 pi squared L over G. And it's not really that different if you plot t squared versus L. 4 pi squared over G gives you your slope. I just like it better because I don't like square roots. But either way is completely fine. So I was telling her this story, and I give this example a lot of doing like t squared versus r cubed for Kepler's third law, or t versus square root of L for a pendulum. Both of those involve a capital T, which is a period, which is a time. And so I was telling her about this friend of mine, and she said, well, okay, but like, what if, time's not linear? And I was thinking, because in special relativity, time is actually not linear. It actually slows down the faster you go, which is really weird and beyond the scope of this class. But it is a true fact, and it is kind of interesting. So I was like, oh, well, according to special relativity, blah, blah, blah. And I started explaining how you would account for that. And she was like, oh, no. I mean, I know time's not linear. It loops around because that's how I could see the future. And at that point in time, I think I decided to give up trying to explain data analysis to a person who thought that time looped around, and that's how she could see the future. I did live with this lady for 3 years, and she's a very sweet lady. But anyway, she thinks she's psychic and can see the future. So that ended our discussion of data analysis for that day. So this is how you can use the pendulum data to calculate G. So what if you don't actually know the relationship? So this is the part where it gets kind of mathy and tricky. So if you're like, I'm good, this is hard enough, I'm done now, that's fine. But this next part involves a little bit more math. So now what we're going to do is we're going to guess the relationship between the period of the pendulum and the length. So I'm just putting in K and A as two constants. I don't know what they are, and we're going to figure out what they are later. I already told you the formula for it, but we're going to pretend we don't know it. And how would we figure that out? So yeah, these are two constants. A is called the power. So instead of being, like, you guys know there's functions that are like x squared or x cubed, this is L to some power, and we don't know what it is. So A could be 1 or 2 or 3, or it could be 0.5, or it could be anything. And then K is just a normal constant in front of the L. So what we're going to do now is we're going to take the natural log of both sides. So we're going to take the natural log of t, and what you do to the left side, you need to do the right side. So you're going to take the natural log of the right side. Now, this is where some of you are going to say, well, what the heck is a natural log? And if you don't know what a natural log is, I think it's time to stop now because you'll learn about it in later math classes. But this is, or you can keep watching and just be entertained with all this discussion of natural logs. But you take the natural log of both sides, and then let's go to a new page so I have room to write. One of the rules of natural logs is that if you have two things multiplied together, you can actually separate them out and add the terms. So we can rewrite the natural log of the whole thing as just the natural log of k plus the natural log of L to the a. Another rule of natural logs is that if you have a power, you can actually bring it down. So I can put the a in front of my natural log of L. And then just for fun, I'm going to rewrite it this way and put down my natural log of t. And now this should look a little bit familiar. I can now put in a y equals mx plus b. This means that I can plot the natural log of t versus the natural log of the length. And this will tell me that the power is going to be the slope of that curve. and the y-intercept is related to the constant. In this case, I don't really care what the constant is. You could figure it out if you wanted to. But what I'm really interested in is what is the power. And so this is a way of figuring out, is the period related to length squared? Is it related to length to the 1/2? You can also do this where everywhere I put an L, put an M. And in that case, you should get that the power in this case should be really close to 0 because M has nothing to do with it. So it should not really relate to it at all. So that is how to linearize data like a physicist. And if you would like to, you can now apply that knowledge and complete the rest of this activity.